Okay, good morning everyone. Good morning. So I'll start a problem on transient conduction. Okay, so we'll solve a problem on transient conduction and then we'll move to thermal radiation. Okay, so problem. And this one particular problem will take care of the different types of cases for transient conduction. Okay. So in this particular problem, we have the tip of a heating element in the form of a cube. This is in the form of a copper cube. I'm just going to draw only the cube, but a planar view of this. And one face of this cube is insulated. And the cube is heated by making use of ohmic heating, which is essentially passing current through a wire. So I have the wire here. Which means that there is some energy generation taking place. And the voltage difference across the terminals of this heating element is 0.5 volts. And then the current that is passed through is 0.01 amperes. .01 amperes, okay? And as a consequence of that, this element gets heated up, which means that the current flowing through this resistive element acts as an energy generation within the heating element. Now this is exposed to ambient on all the 5 sides besides the insulated one. Temperature of the surroundings are given to us. Ambient is also given to us. And this is T surrounding, and the following properties are all listed for us. So thermal conductivity of the copper cube is given as the following. .388 watts per meter Kelvin. T infinity and T surroundings are around 16 degrees. Celsius. Then some material parameters, emissivity of the surface. This is for the copper. Is given as 0.8. Then we are given the density or the specific gravity of copper. Sg is specific gravity, which is the ratio of density of copper to the density of a standard, typically water. Okay, so this is rho of copper not to be confused with specific weight, which is weight per unit volume. Okay, so this is given to us as 8.933, so that the density of copper is density of water times that value, which is 1000 times 8.933. So rho of copper kg per meter cube. Okay. Specific heat for copper, C so many joules per kg Kelvin, and then the convective heat transfer coefficient for ambient atmosphere, H, is 20 meter square Kelvin. It's a cube, so the dimension of one of the sides is given as 1 millimeter. And we are asked to do the following. Okay? So first part, obtain the Biot number and then decide whether this satisfies the lumped capacitance or zero-dimensional conduction problem. Okay, so what is the Biot number? The second thing is, for this most general situation where I have thermal radiation, convective heat transfer, and also energy generation within the copper element, what is the differential equation? So general ODE of the system and you are told that initially the copper is at a temperature of 300 Kelvin. So T mixed units, some temperatures are given in degrees Celsius, some in Kelvin. You either operate in degrees Celsius or Kelvin depending on the type of the mode of heat transfers involved. If radiation is present, Kelvin, no questions asked. If it's only convection, then we can convert everything into either degrees Celsius or Kelvin. Okay? So general ODE of the system. Then if you assume convection is negligible, if you assume heat generation is negligible, and if you assume T surrounding to be negligible, what's the solution for the ODE? So T surrounding, convection, and then E dot G. Neglect all these three. What is the system solution? So ODE plus the solution. And then the last case is the most important one for us, where we make use of convection and energy generation. It's more relevant to our situation. So for negligible, radiation, heat transfer, obtain the system solution. T is the function of T, and then what is the temperature of the cube after 1.5 seconds? And the Biot number is to establish whether we can assume a zero-dimensional conduction. Okay. All right. So we first find out the Biot number. Okay, by making use of the typical canned formula, which we have seen in the previous lectures. And when you are calculating the Biot number, keep in mind that one face of this cube is insulated, and so when you are calculating the characteristic length, you have to look at the area available for heat transfer, which means this is sans one face of the cube. There are 6 faces for a cube, and so I'm going to consider only 5 faces for heat transfer taking place. Okay? So first step, calculate the Biot number. H LC by the thermal conductivity K. If this number ends up being less than 0.1, we decided last time, then zero-dimensional conduction is valid. Okay. The characteristic length is the ratio of the volume to the surface area for heat transfer. Okay, so that A suffix S is the total surface area for heat transfer, not the insulated side. So if I calculate the Biot number, H is given to me 20 watts per meter square Kelvin. This is 20. The characteristic length is the volume by the surface area. Volume of a cube is the cube of its side dimensions divided by the surface area, which is 6 times the square of the side, but I have only 5 sides to be included, 5 faces to be included. So 5 times that's going to be the characteristic length, the ratio of the volume to the surface area, divided by the thermal conductivity, 388 watts per meter Kelvin. You crunch these numbers, it will end up being very small. It's 0.0000103, which obviously tells us that this is going to be a situation where I can assume zero-dimensional conduction. Okay? So it is essentially as if the temperature gradient within this cubic body is so negligible. Right, so this is less than 0.1. Even though we solved partially the one-dimensional unsteady conduction problem, we will not be solving any problems on that. Okay, so that was just meant as a way to mathematically show that if I have a Biot number of less than 0.1, which comes from the 1D unsteady conduction, then I can assume zero-dimensional conduction. Zero-dimensional conduction implies that temperature is a function of time only. Okay? And so that's the first part of the problem. Second part of the problem, and once again these are very standard steps, so there is no secret involved here. The second part of the problem is something that I briefly touched upon last class before we dispersed, but I'm going to talk about it once again very quickly. Start with the first law. So temperature is a function of time only, and E dot stored is E dot in, E dot out, plus or minus E dot generated. For E dot generated, if I know the current flowing through the wire and if I know the voltage difference across the terminals, then the power dissipated is the voltage times the current. Okay, so V times I, it's a standard formula. So this is E dot G. Notice in this problem you are not given the volumetric heat generated. This is V times little I, where V is 0.5 volts. And the current I is 0.01 amperes. And the product of these two will give you watts. So this is 0.5. 0.01, and so E dot G is 0.005 watts. This is not the same as Q dot times capital V. Q dot is volumetric energy generation, so energy generated per unit volume. Capital V is volume. You can of course obtain Q dot if you know E dot G. Okay, so something to keep in mind. Maybe something I'll write here. So that's energy generated. E dot E dot stored is not at steady state, so I have to include that term. So E dot stored is m times c times dt by dt, the exact differential, because we are assuming temperature is independent of any spatial dimension. E dot in and E dot out. This is where you make a judgment call, and then you immediately recognize that the initial temperature of this cubic element is greater than the ambient temperature, it is greater than the surrounding temperature, which means that there is going to be some heat loss from the cubic element onto the ambient in the form of convection and in the form of radiation. Right? There is going to be a certain amount of energy emitted by this cube. But at the same time, there is also irradiation on the cube from the surroundings. That's going to be the energy that's coming into the cube. Okay, so if I write E dot in, this is going to be, and if you assume a large enclosure with gray surroundings and surface, it's large and gray surface. And you'll see all of these being proved very soon using Kirchhoff's laws for radiation heat transfer. So E dot in is going to be alpha times the net irradiation times the surface area available for heat transfer. Alpha is the same as epsilon if you have a gray surface. And G can be approximated using the Stefan-Boltzmann formula for the surrounding. And so E dot in is sigma epsilon a suffix s T surrounding to the power 4. This is the energy incident on the body, but a portion of that is absorbed, which will enhance the thermal energy of the body. Okay. E dot out is going to be convective heat transfer, so Newton's law of cooling, H a suffix s T minus T infinity. Then there's going to be a certain amount of emitted radiation, which we are going to touch upon today and then for the rest of our semester before going into convection. And so sigma epsilon a suffix s T to the power 4. Capital G is irradiation. This is the emitted flux multiplied by the surface area. E is the emissive flux. Put everything together. mc dt by dt is E dot n, which is sigma epsilon T surrounding to the power 4 minus plus V times I. Excuse me. Does this make sense to everybody? Standard energy balance, first law, essentially. What have we done so far is we have looked at conductive heat transfer. We are slowly getting our feet wet into convection or radiation, and then eventually we'll come to convection. There is nothing big in convection except the calculation of this little creature H, which is the biggest issue. Okay, but radiation involves a lot of other facets. Alright. So if I rewrite this in a much nicer way, bring in all the T's onto the left hand side, here is what I have. So mc dt by dt sigma T to the power 4 function of time plus h times T of T is sigma epsilon surrounding to the power 4 plus where I'm just calling that product as E dot G. So this is the most general ODE. It's a nonlinear ODE, difficult to solve. It's nonlinear because of this t to the power 4. Okay? But for special cases, one can come up with a solution, which is what I'm going to do next. I'm going to ignore convection, I'm going to ignore energy generation, and we're going to say that the surrounding temperature is negligible, so the irradiation from the surrounding is fairly minimal. But there is still some amount of emissive flux coming from the copper element itself, so that will be included. So that's my third part of the problem, so that's part C. If I do the following, take a look at the general ODE. I'm ignoring convection, so those two terms cancel off. I'm ignoring energy generation, so the last term drops off. And then I'm ignoring the surrounding temperature. This is once again an order of magnitude analysis. So that also drops off. And so I'm left with the following ODE. So MC dt by dt sigma epsilon a suffix s is equal to 0. I have some initial conditions. T at t is equal to 0. T naught. This can be solved, okay, by just basic rearranging. If I look at MC is a constant, sigma epsilon times AS is a constant, so I essentially have some big constant this is the ODE I need to solve. And I can do that by the following manner. Okay, t to the power 4, if I divide through and rearrange things, so this is dt by t to the power 4 is minus 1 by c dt. Essentially cross multiplying and rearranging. And then integrating between the limits from t naught to some time t. I should really be using dummy indices, dummy variables inside the integrand, but for the time being, just bear with me. And integral from 0 to t. The left hand side can be integrated. Right hand side is obviously fairly trivial. So I have minus 1 by 3 t cube t naught to t. I'm not going to go through the details of the integration, this is fairly straightforward. This is equal to minus 1 by c from 0 to t, little t. Little t is time, capital T is temperature of the heating tip, the heating element, which is the copper cube. And if I rearrange things, I end up getting the following. E is going to be, the negative sign cancels off, okay, so I'm going to have this factor of, this cancels off here. There's a lot of miscellaneous stuff going on outside. There's 3 by c, if I rearrange everything, and then I end up getting the following. So 1 by t naught cube, and then 3t by c. Whole to the power 1 by 3. This is of academic interest. I'm not interested in solving for the temperature. It's not going to change by a whole lot. Okay. And the character C contains all of the constants that are involved, which is mass times the specific heat, and then I have sigma epsilon and A suffix s. Okay. So this is just for saying that under special situations, when you have radiative heat transfer, the equation can actually be solved for. The temperature profile can actually be obtained. And if you look at your book, they also have the solution for T surrounding not negligible, which essentially is just a constant stuck in there. That's not a big deal. But it just looks very messy, so I did not do that. This is good enough for us for the time being. Alright. Last part of the problem, which is the more important part. So neglect radiation. Which is kind of funny because we're going to spend the next 15 lectures on radiation. Okay. I have convection, I have heat generation as well. So if I write my ODE, now I end up with the following. MC dt by dt. This is equal to h times A suffix s negative sign T minus T infinity plus E dot G. I divide through by this h by A suffix s and I get the thermal time constant, so I have mc by, and instead of t, I'm going to do a change of variables and call it as theta, as t minus t infinity. So say which means theta naught is T naught minus T infinity, just a change of variables. So this is d theta by dt plus theta. This is equal to E dot G by h times AS. So this becomes my first order ODE, fairly straightforward. Be careful, there is initial conditions. The right hand side is non-zero, so which means that there is a step input to the problem. As soon as the time is switched on, there is this constant volumetric energy generation which acts as a step input to the system. Okay? So under the initial conditions, theta is theta naught. MC by this quantity, we looked at it last time. MC h times AS is density times volume times specific heat capacity by h times AS. Volume by the surface area is my characteristic length, and so I call this as tau rho LC C by h. This is the thermal time constant. And so my ODE becomes the following. Tau plus theta is and tau is the thermal time constant. With your permission, I'm going to skip a few details now. This is just solving this first order ODE. My notes will have all these details posted. Please take a look at it. In system dynamics, you would have had two types of responses to a system. Free response, which is the response to initial conditions. And then forced response, which is a response to an input. In this situation, this is a constant. H and AS are all constants. So this is a step input. And the response of a system to a step input can be very easily obtained using Laplace transforms. I'm going to skip all those details. I have it in my notes. Please take a look at it if you'd like. So theta of t, after solving, is going to have two pieces. The free response, which is theta naught e to the power minus t by tau. This is the response to the initial conditions. And then the response to the step input can be written in the following manner. This is the magnitude of this step input times 1 minus e to the power minus t by tau. This is the forced response. Does this make sense to everybody? You remember these things from system dynamics vaguely? Okay. But this is generic, so for any kind of a system that we are studying in transient conduction, which is zero-dimensional conduction, if I have convective heat transfer, if I have energy generation, this is my solution. That's it. Don't need to do anything else. If I have negative energy generation, this becomes minus Eg. If I have positive energy generation, it's plus Eg as written here. Tau is the same character that we have found out there. Substitute. Be careful, theta is the change of variables that you've introduced. So if you really want the temperature of the cube, T is theta of T plus T infinity, so please be careful there. So that my final solution for convection plus energy generation, my final solution is the following. So T of T. And unless I ask you to derive something, you can appropriate this. Okay? So T of T is T infinity plus T naught minus T infinity e to the power minus T by tau. T naught minus T infinity is theta naught. And then I have E dot G H times AS 1 minus e to the power minus T by tau. System response. For our particular situation, I started off at initial conditions that were more than the ambient temperature. So I start off here. T naught. And then it should be quite obvious that in the limit of t, time tending to infinity, the exponential terms will drop off. So this term will be gone, that term will be gone, and essentially I'm just going to reach steady state temperature, which is the ambient temperature. And the drop is going to be exponential. So this is T infinity. This is going to be an exponential solution. And when time t is approximately, does anybody from system dynamics remember what is the time it takes to reach approximately steady state? Any other answer? Any other answer? Yes?
Is it 4?
4 tau. We reach up to approximately 98% of steady state. Okay? If the initial temperature is lower, then the curve will just be mirror image of it, whatever is drawn here. Very last bit of the problem, just some plug and chug. Your homework is nothing more than this, okay? For the conduction, zero-dimensional transient conduction, at least it's all mostly this. So at t of 1.5 seconds, I need to calculate my thermal time constant. If you plug in the values, this is approximately 34.3 seconds after you do the plugging in of all the values using the expression for tau, and with all the initial conditions and so on, T at 1.5. Because I'm using only convective heat transfer, it does not matter whether I'm using degrees or Kelvin. But because initial condition is given in Kelvin and T infinity is in degrees Celsius, I have to do one or the other. So keep it in Kelvin if you will. This is T infinity, which was 16 degrees, so 289 Kelvin. Then I'm going to have plus 300 minus 289 e to the power T by 34.3, and then the last bit plus E dot, which was 0.005 by 20, 5 times 1 millimeter square is the total surface area for heat transfer, and then 1 minus T by 34.3. All of this at T of 1.5 seconds. Would the temperature have changed by any much of a value? Probably not a whole lot, because tau is 34.2 seconds. So at 1.5 seconds, I'm not even sitting at a fraction of tau. Okay, so the temperature is approximately going to be the same as your initial temperature. Not much of a change. Okay. I don't have the final numbers, but I'll post the numbers on your column page. Okay. So things we've done so far. We started off with basic heat transfer, where we looked at conduction, convection, and radiation. We started solving some problems. Then we looked at one-dimensional conduction, steady state. We obtained the heat diffusion equation in steady state conditions, applied it for a variety of problems, and then we said, okay, we can use a resistor network if we assume steady state and uniform temperature, where the heat generation is essentially zero. Then we walked into zero-dimensional conduction, where we said, okay, it's no longer steady state, but there's no spatial dependence. And that was the end of the conduction road. Okay. Now we're going to move to radiation heat transfer. The biggest issue that I feel with radiation heat transfer, at least the difficulties that I've seen people encountering as a student in this class, is radiation comes with a lot of definitions. And that is just the nature of the beast. There is no way around it. But if you keep certain things straight in your mind, then radiation is fairly straightforward. Okay, and you'll see as we solve some problems and look at it. So to motivate the presence of radiation heat transfer, let's conduct the following thought experiment. I have some kind of a chamber, okay, and let's say the chamber walls are at temperature T surrounding. And let's say that the chamber is evacuated, so there is vacuum present. And let's say that before the evacuation happened, there was an object present within the chamber at a finite temperature. Temperature T of T. So, what happens? There is no medium within the chamber, which obviously means there is no conduction. And there is also no convection, because there is no bulk motion, because there is no medium present. But if one performs an experiment where the temperature of the body can be monitored as a function of time, and we are not interested in those details, what one will realize is that the temperature of this object, which is present inside the evacuated chamber, is going to decrease. If it is assumed to be greater than the surrounding temperature initially, let's say, it's going to decrease as time goes on. And eventually it will reach thermal equilibrium. Right? Temperature of the body is going to be the same as the temperature of the surrounding wall. in the absence of any medium itself. So which tells us that there is this third mode of energy transfer in the form of heat, which is taking place independent of the medium that is present between two interacting bodies. And this mode of heat transfer is radiation heat transfer. Okay, so fundamental difference, whether I talk about conduction or convection. In conduction, I need a medium but no bulk motion. In convection, I need both. And for radiative heat transfer, I need neither. Between the interacting bodies, of course, I of course need an object and a surface. Otherwise, what am I talking about, right? So for radiation, no need for a medium, no intervening medium required. It can take place in the presence of a medium as well. It is just that the absence of a medium heightens radiation heat transfer. Okay? And what I want to do for the rest of the next 10 minutes or so is I want to set up the foundations for radiation heat transfer. A lot of major fields, figures in the field of physics have been responsible for the development of radiation heat transfer. The first and foremost is James Clerk Maxwell. So he laid the foundations for radiative heat transfer. And then after Maxwell, Albert Einstein, Max Planck, Marie Curie, all of these were instrumental in bringing radiation heat transfer to the forefront of technology. Not that that was their desire was more curiosity. It is our selfish desire, we use them for technology. Okay? So Maxwell, in 1840s to 1860s, during that period of time, Maxwell postulated that matter emits energy because of changes in its internal atomic configuration. Okay? So Maxwell, matter emits energy due to changes in its internal atomic configuration, and this energy is emitted in the form of electromagnetic waves. Or what is more succinctly called electromagnetic radiation. Okay? And because of the fact that the energy is emitted and transmitted in the form of waves, it is quite obvious that the intensity of the energy emitted should be a function of the wavelength of these waves. And so it behooves to study, first of all, the entire electromagnetic spectrum, which contains a whole list of wavelengths, and then what we will do is we will slowly shrink it to a region of interest for us as mechanical engineers. Okay, so this implies that the energy emitted is a function of wavelength. And so I'm going to draw the electromagnetic spectrum now. Which contains a list of waves. Okay, so lower end to the higher end. Here is the now these are plotted in the order of increasing wavelength in the units micrometers. So lambda is a wavelength. Electromagnetic waves travel at the speed of light, so you can see that they can be related to their frequency using the speed of light. So higher the wavelength, shorter the frequency. smaller the frequency. Okay? So this is an increasing wavelength, so starting from around 10 to the power minus 9 or 1 nanometer all the way to 10 to the power 10 micrometers. Okay? What we are interested in is a region which ranges from 0.1 micrometers to 100 micrometers. So for us, micrometers to 100 micrometers. All the waves beyond 0.1 micrometers on the lower end of the spectrum, they will be occupied by these gamma rays and then X-rays. So here I have gamma rays, X-rays. Gamma rays are typically emitted during nuclear reactions. If you'd like to recreate X-rays, then you take a metal conductor and you bombard it with very high-speed electrons. Okay. On the higher end of the spectrum, you're going to have radio waves, microwaves, the things in your microwave oven, microwaves, they're produced by an electronic tube, magnetrons. Then you have radio waves. Their wavelength is much higher. Radio waves can be produced by exciting a crystal, or if you pass alternating current through a metal conductor, you can generate radio waves. They are not of our interest. Our interest in the spectrum is this region called as the thermal radiation region. So this region right here. In this particular region, the thermal radiation region, which extends from 0.1 micrometers to around 100 micrometers, the radiant energy is emitted as a consequence of the temperature of that matter. And because of this, there is going to be some changes in the atomic configuration. Okay? So that's what our interest is. Thermal radiation is radiant energy emitted due to temperature, which causes oscillations of the atomic field. And in this region, there are three things of interest to us. The first is the ultraviolet region, a part of which falls in the thermal radiation range. So around, let's say, up till 0.3 micrometers, and then this goes up to 10 to the power minus 2 micrometers. You see that this range from 10 to the power minus 2 micrometers to 0.3 is occupied by ultraviolet rays. Right at 0.3 or 0.35 or 0.4 is where the wavelength of violet color starts. And it starts all the way and ends at around 0.7 micrometers, which is where the red color wavelength is. So that is the visible spectrum. And once you go past the visible spectrum, you end up with the infrared spectrum. So all this is infrared. And so what this tells us is the following. The thermal radiation range includes a portion of the ultraviolet spectrum. Ultraviolet rays are dangerous, they kill microorganisms. A portion of the thermal radiation range includes visible light. So visible light is nothing but radiant energy which falls on our eyes and creates the sensation of seeing, the perception of sight. And then I have infrared, which is not visible to the human eye, but we can generate things that make it more visible. And the most important thing is that the sun, which is the source of light, tells you that the range of wavelength that is emanating from the sun falls in this thermal radiation range, because you are able to see the sun. It's visible light. Okay, so if I look at it, the sun or solar radiation, the spectrum of solar radiation starts at around 0.3 or 0.2 micrometers all the way to 3 micrometers. So the lower end of the solar spectrum falls in the ultraviolet range, which is the dangerous part of solar radiation. The higher end of solar radiation falls in the infrared region, and obviously as I go lower and lower, the energy that is radiated is going to increase. So when I'm in the ultraviolet region, there is greater energy that is coming through. If I look at a nuclear reaction, there is a large and humongous amount of energy going through, so you can see that gamma rays and X-rays, there's huge amounts of radiant energy that is emitted during this process of creating these rays. Okay? So it makes sense for us, because the sun is our major source of light, and because of the fact that the sun spectrum is a part of the thermal radiation spectrum, it enables us to give a little more of a positive spin in studying radiation heat transfer. Okay? Because this is stuff that we are seeing every day. So it should pique our curiosity to understand what's going on. Alright? So we will restrict ourselves to these two ranges of wavelength, 0.1 to about 100 micrometers, and in that the sun or solar radiation forms an important part. Alright. And the sun is important in many ways because, of course, it's our major source of light, but it also acts in some way at certain values of the wavelength. It acts as an ideal body. And by understanding the sun as an ideal body and by enacting principles of thermal radiation on that ideal body, it is possible for us to experimentally obtain what can happen on a real surface. So that's where our motivation is in looking at solar radiation. Okay? Now before doing that, we have to, before going into thermal radiation and starting to look at some of these relationships, we need to have some assumptions. Okay? So first one, we will fix the lower and the upper bounds as 0.1 micrometer to 100 micrometers.